Welcome to iLecture Online, and here's another example of how to use Coulomb's law to solve problems dealing with charges and finding forces between the charges. And here we have something that's a little bit more complicated, so let's take a read and see what it is. It says here that we have a 6 microcoulomb charge that is placed at the origin, and a 4 microcoulomb charge that is placed 2 meters to the right. But then there's a third charge, a minus 8 microcoulomb charge, which is placed on the y-axis 2 meters above the first charge. What is the force on the second charge due to the presence of the other two? All right, let's make a drawing of this. Let's draw a y-axis and an x-axis. There we go. And let's place these charges on them. So we have our first charge right here. That's a positive charge. And we'll call that Q1, and that's equal to 6.0 microcoulombs. It's positive. We have the second charge, 2 meters to the right, so let's say that's here 2 meters to the right, a negative charge, Q2, which is equal to minus 4.0 microcoulombs. Then we have a third charge. That third charge is placed right above on the y-axis on Q1 and also 2 meters away. That's also a negative charge, so we call that Q3, which is equal to minus 8 microcoulombs. And so the question then asks, what is the force on the second charge due to these other two charges? All right, how do you start on something like this? Well, the first thing you want to do is draw vectors representing the forces on Q2 due to the presence of these other two charges. So for the presence of Q1, what happens to Q2? Well, since they're oppositely charged, Q2 is attracted to Q1, so there's a force in this direction, and let's call that F. And to indicate that this is the force between Q1 and Q2, what I do is I go F1 comma 2, so I know it's a force between these two, and it's in the left direction. Okay, so now we have another charge, and so how does this charge affect this charge? Now, since they're both negatively charged, they repel each other. And so that means that this charge pushes against this charge in this direction. And so we have a second force in this direction, call that F between 2 and 3. And that gives you kind of a visual explanation as to those forces, what those forces are. Now, what it ends up being is simply a vector sum of these two forces to find out what the net resultant force is. And before you get started on that, you may want to say, well, let's see. I want to have kind of a visual picture of how big these forces are. This is an 8 microcoulomb force and a 4 microcoulomb force. They're both negative, and so they're about this far apart. And this is 6 and 4, and they're a little bit closer together. So it looks like the magnitude of force is probably about the same, so I want to give it a fairly good visual picture that is reasonably correct on the magnitude of those two forces. So I can graphically now say, well, the sum of these two forces graphically, using what we know as the parallelogram method, you can then see that the net force or total force, F total, would be kind of like this. So that's what we're looking for. That's the answer. And of course, to find the answer, we then have to find the magnitude of that force and the direction of the force. For example, we want to find the angle, let's call it phi, between that force and the x-axis in that direction. All right, so how do you go about doing that? Well, the first thing you want to do is actually find the magnitude of these two forces. So using Coulomb's law, we can say that F1, 2 is equal to, and I'm going to write it like this to indicate again that I'm finding the magnitude of that force, not the magnitude in direction, simply the magnitude. It's a scalar quantity. It's kind of like the absolute value of that result, and it always will be positive. And so this is equal to K times Q1, Q2 divided by the distance between 1 and 2 squared. Now again, I use this subscript 1 and 2 to indicate that I'm looking for the distance between those two. And this is equal to 9 times 10 to the 9th newtons meters squared per kilogram squared. Well, not kilogram squared. I keep thinking about Newton's law, but no. Here we're dealing with charges, so it's Coulomb squared. Multiply times the magnitude of the first charge. That's this one right here. So it's 6.0 times 10 to the minus 6 coulombs, because micro is 10 to the minus 6. The second charge is 4.0 times 10 to the minus 6 coulombs. And again, even though it's negative, I put a positive quantity in because that is just the magnitude that we're looking for. And then the distance between them squared, we realize that this distance here is 2 meters. So we write 2.0 meters quantity squared. And then we grab our calculator to find out what the magnitude of that force is. So plug in the numbers. So it's a 9e to the 9th times 6 exponent to the 6 minus times 4e to the 6 minus equals. And then we divide that by 2 squared, so that's 4. And the answer, where did my pen go? The answer then becomes 0.054, and that would be newtons. The force is in newtons. Notice that the coulombs squared cancel out and the meters squared cancel out, so we're left with newtons. So that's the magnitude of force between those two charges. We do the same for the other two charges. We now want to find the magnitude of the force between those two. So we can say that F between 2 and 3. And again, I indicate that it's the magnitude that we're looking for is equal to K times Q2 times Q3 divided by the distance between them squared. So again, I will indicate that the distance between them squared is R2, 3, subscript 2 and 3. Now, what is this distance? This is R2, comma 3. What is this equal to? Well, since we know that this distance is 2 meters and that distance is 2 meters, and that's a hypotenuse, we can kind of use Pythagorean theorem. We can say that that distance is equal to the square root of 2.0 meters squared plus 2.0 meters squared. Remember that the magnitude of a diagonal of a square or any triangle is equal to the sum of the squares of the two sides. So this would be equal to the square root of 4 meters squared plus 4 meters squared, which is equal to the square root of 8 meters squared. And so it's equal to the square root of 8 times meters. All right. Now, plugging in the values that we have, this is equal to 9 times 10 to the 9th newtons meters squared per coulomb squared times the charge 2. Charge 2 right here is, again, I use the positive value, times 10 to the minus 6 coulombs. Then Q3, which is over here, I use 8.0 times 10 to the minus 6 coulombs, and take the whole thing divided by the distance between them squared. So that would be the square root of 8 meters quantity squared. All right, now we can go ahead and use our trusted calculator to find out what that is. 9e to the 9th times 4e to the 6 minus times 8 exponent 6 minus equals, and then divided by the square root of 8 squared. Of course, the square root of 8 is 8, so divided by 8 equals, and the magnitude there is equal to 0.036 newtons. Again, the meter squared cancels out and the coulomb squared cancels out. All right, so now we have the magnitude of F12, we have the magnitude of F23. What do we do next? Well, since we're going to have to add them as vectors, we can't add just these two numbers together. They're pointing in different directions, so to solve that, we have to find the x and y components of each of those vectors. Now for F12, that's fairly easy. We can say that F1, the magnitude in the x direction, or I should say F12, not F1, but the force between 1 and 2 in the x direction, that is simply equal to the magnitude of that, because the force is pointing in the x direction, so the magnitude of that is equal to 0.054 newtons. You say, well, wait a minute, isn't it pointing to the left? Shouldn't that be negative? Again, since we're looking for the magnitude, it's just a positive quantity. It's an absolute value. Now we have to do the same for F23. Now here it's a little bit more tricky, because we have to find the x and y components of that force. So in other words, here this would be the F23 in the x direction, and here this here would be the F23 in the y direction. We then have to realize what this angle is. This angle here is theta. Now here it's fairly simple on the angle because we know that this is a side that's equal to 2 meters. This side is equal to 2 meters, so we know that this is directed 45 degrees below the horizontal. This is therefore 45 degrees. So we can say that this angle here is 45 degrees. So we can say that theta is equal to 45 degrees. All right, knowing that, let's find the x and y components of F23. So F2, 3 in the x direction is equal to, and again, I'm only looking for the magnitude so far. So that is equal to the vector F23, or the magnitude of the vector, times d, since the x component is adjacent to the angle of this particular triangle, we can say that is equal to the cosine of theta. And so this is equal to the magnitude of F23, which is right here. It's a good thing that we label the subscripts of what these forces are, otherwise we get confused. So make sure you use a good labeling technique. So it's 0.036 newtons times the cosine of 45 degrees. And so times 45 cosine equals, and so this becomes 0.025 newtons. So that's the x component of F23. Now we do the same for the y component. So F23 in the y direction is equal to F23 times, in this case, since we can move this vector over here, that would make it opposite to the angle theta. We can say that's equal to times the sine of theta. All right, plugging in the numbers here. We can say that this is 0.036 newtons times the sine of 45 degrees. And of course, we should know that the cosine of 45 degrees and the sine of 45 degrees is the same. So we'll get the same answer, 0.025 newtons. Okay, now we have all the components of each of the two vectors. We have the x component of F12, the y component of F12 is 0, so we don't need to calculate that, and we have the x and y components of F23. Now to find the resultant vector, we need to add the x components and the y components together. So we can now say that F total in the x direction. So we're going to find the x and y components of the resultant or total vector. Now be careful here. Now we don't want the magnitudes anymore. Now we actually want to add the components together. And so when we add the components together, we have to realize we have to deal with the directions. So I can see here that to find F total in the x direction, I need to add this vector with this vector together, because those are the only two components in the x direction. And notice that this is in the negative direction, so F total x is going to be the minus quantity of this, minus 0.054 newtons in the x direction. So I'm adding this component, pointing to the left, plus I'm adding that component that's pointed to the right, plus, and that component F23, we found what it was equal to. It's 0.025 newtons in the positive x direction. Okay, so when we add those two together, I can say that the x component of the total force is equal to minus 0.029 newtons in the x direction. Okay, now we do the same for the y component. So we have the total force in the y direction, which is equal to, now notice there's no y component on our first force, and there's one y component on the second force. It's pointing downward, so we know that's going to be negative quantity. Here it is, F23 in the y direction, so it's a minus 0.025 newtons in the y direction. Nothing else to add, so now we know that here is the magnitude of the y component, here's the magnitude of the x component. So we can now write the answer as F total, which is equal to the sum of the x and the y components. So we have the x component right here, which is minus 0.029 newtons in the x direction, minus 0.025 newtons in the y direction. And here is the force the total force on Q2 due to the presence of the other two charges. Now that's the answer in the vector form, in a vector quantity. But what if I simply want to find the magnitude of that force? Well, to find the magnitude of the force, you use Pythagorean theorem. You can say that F total, the magnitude of that, is simply equal to the square root of the sum of the squares of the individual components. So that would be equal to the F total in the x direction squared plus F total in the y direction squared. So to simply take the square both components, we sum them together, take the square root, and that gives us the total magnitude. So this would be equal to the square root of the x component, which is minus 0.029 newtons squared, plus, and then we take the y component right here, which is minus 0.025 newtons, and we also square that. And what do we get when we calculate that? So we get 0.029 squared that plus 0.025 and square that, add them together, take the square root, and we get that's equal to 0.038 newtons. So that is the magnitude of the resultant or total force. And then finally, I'm running out of board space, but I think I could squeeze it on the side there. I now would also like to know what this angle is right here. So this angle is made up from the x and y components of the total force. So here we have the x component, and maybe I shouldn't use blue. Let me try this color right here. So here we go. There's the F total in the y direction, and here is the F total in the x direction. So those are the two components of the final resultant, the final total vector, the force on charge 2. How do we find that angle? Well, we can find that by taking the arctangent. This can be like the opposite to the angle. This can be the adjacent to the angle. So we can see then that the angle phi is equal to the arctangent of the opposite side. Now the opposite side to the angle would be this component. When we move it over here, that would be F total in the y direction, or at least the magnitude of that, and divided by the adjacent component. So that would be F total of the x direction. So this is equal to the arctangent of F total in the y direction. That's this one right here. And of course, we only care about the magnitude. So that's 0.025 newtons divided by the F total in the x direction. That's this quantity right here. Again, we only care about the magnitude, 0.029 newtons, like so. And when we plug that into our calculator, what do we get? So 0.025 divided by 0.029. And then we take the arctangent of that. And we get about 41 degrees. So it's equal to 41 degrees phi. There we go. So there's two ways of looking at this answer. We found the resultant vector. This is the resultant vector. The total force on Q2 is equal to negative 0.029 newtons in the x direction minus 0.025 newtons in the y direction. So we wrote it as the sum of its components. Or you can think of it as the magnitude. This is the magnitude of the force, and that's the direction of the force relative, in this case, to the negative x-axis. And that is how you do one of these problems. They're very lengthy, but just to quickly summarize how you go through this problem, you first make a diagram of where the charges are. Then you draw the forces on the charge in question, and you want to find the force on this charge relative to the presence of the other two. So you draw a vector representation using the arrows of what those forces are, and then you have to sum them together, which means you have to find the magnitude of each of the two forces. So you find the magnitude of the one force, find the magnitude of the other force, then you find the x and y components, and then you add the x and y components together to find the total force. Okay, give that a try and see if you can work it out. Good luck.